Okay, so today we'll be solving problem number 17 of exercise 2.2. We have a, m and n positive integers with m not equal to n. So we need to prove that if m greater than n, then a power 2 power n plus 1 divides a power 2 power m minus 1. And then we need to find the GCD of a power 2 power n plus 1 and a power 2 power n plus 1. So let's do the first part. Now, when we look at a power 2 power m minus 1, we notice that it is similar to x square minus 1. So the intuition here would be to use difference of squares in some way to prove the divisibility. Since we know that x square minus 1 factors into x minus 1 and x plus 1. So x plus 1 divides x square minus 1. So here the x plus 1 would be analogous to a power 2 power n plus 1. And the x square minus 1 would be analogous to a power 2 power m minus 1. So we need to write a power 2 power m in the terms of something whole squared. So we can write it as a power 2 power m minus 1 times 2 in the power, and that is equal to a power 2 power m minus 1 whole squared. So a power 2 power m minus 1 can be factored as follows, again by using the difference of squares. Now you notice that on the left hand side, the a power 2 power m minus 1 is the same as a power 2 power m minus 1 whole minus 1, just that the only difference is that the power have changed from m to m minus 1. So we can again factorize a power 2 power m minus 1 whole minus 1 as follows. Now you'll notice that the terms which have a plus 1 remain in the factorization, while the terms that have the minus 1 are factored further. So again, the term that has the minus 1 can be factored further to a power 2 power m minus 3. Now, all the terms which have plus 1 remain in the factorization, and this continues until we reach n. Now, since a power 2 power n plus 1 is in the factorization of a power 2 power m minus 1, we can say that a power 2 power n plus 1 divides a power 2 power m minus 1. Now let's do the second part. So we need to find the GCD of a power 2 power m plus 1 and a power 2 power n plus 1. Now the key identity that we'll be using for this problem would be the GCD of x comma y is equal to GCD of x minus ky comma y for some integer k. The main reason that we're using this identity, or that we get the intuition to use this identity, is because in the first part we proved that a power 2 power m minus 1 is a multiple of a power 2 power n plus 1. So the GCD that we need to find can be written as GCD of a power 2 power m plus 1 minus a power 2 power m minus 1, since it's a multiple of a power 2 power n plus 1. Now this part is equal to 2, so it equals GCD of 2 comma a power 2 power n plus 1. Now this GCD can either be 2 or 1. If a is odd, then a power 2 power n would be odd, because any odd power anything is odd, and so the GCD of 2 comma a power 2 power n plus 1 would be 2. And if a is even, then a power 2 power n would also be even, and so a power 2 power n plus 1 would be odd. So the GCD of 2 comma a power 2 power n plus 1 would be 1.